Okay, let us start. Welcome you. I welcome you for today's this week 6 live session of Economic Operation and Control of our System course. We'll follow the same agenda. We will try to first go through the overview of week 6 and then take questions. These are the deadline for assignment 6 and 7. So tomorrow is the deadline for submitting assignment 6. And September 11th is the deadline for submitting assignment 11. Assignment 7. And this is the same link where you can access all the recordings. So starting with the week 6. Week 6, all these things were discussed. Week 6 was more, entire week 6 was about the production cost modeling. All the concepts which we have studied till now in all the weeks, starting from economic dispatch, then unit commitment, and hydrothermal scheduling. All these things are included, it's used in this production cost modeling. We did economic dispatch, you considering the RAM consent. Initially, we started with economic dispatch for a single time block or a single time instant. Then we moved to economic dispatch with ramping constraints, where we consider a time horizon, let's say for 1 day, just for 1 day. And then unit commitment with more constraints apart from these ramping constraints, startup, shutdown cost, then minimum uptime, minimum downtime. This can be even more than 24 hours, 3 hours or so. Then we saw at hydro plus thermal. So far, using dynamic programming for us or 1 day. Now, if all these things, if this unit commitment is used here in production cost modeling, it has different usage. Can be the usage, the time horizon where these are used can vary from 1 week to even 30 years. 1 week, this will be for operational purpose. Operational and near time. Near future planning. Is 30 years or 1 year to 5 year, 1 week to 5 year can also be used for this fuel budgeting. Depending upon the application, the time which is used, it can change. It varies. And this 10 to 30 years is generally it's a use for planning purpose. Future planning, how when the load increases after 10 years with a forecasted or projected load profile, what will be the generation, optimal generation schedule? Will it be able to meet the load? So we check the reliability indices. If load to be served is greater than the available generation, then there will be load curtailment. The system reliability will reduce in this case. In this case, the reliability will reduce. So there are different types of reliability metrics which we use, metrics, indices. So one which we use in this probabilistic reduction is probabilistic. Even in for deterministic case also we can calculate these reliability matrices. This one is loss of fluid probability. What is the probability that there will be the load curtailment or the load will be lost? It will not be served. Then energy not served is another. So this will, let's say in one day, we have 24 hours. And for, let's say, any these 2 hours, let's say 11th and 20th. For these 2 hours, there is a load curtailment. The y-axis is load curtailment. In this case, probability loss of load will be 2 divided by 24 for that particular day. 1 by 2. This will be loss of fluid probability. So we can say 2 hours in 24 hours or 2 hours per day. Okay. And then this will tell only the number of instances or the number of hours the load is not served. But it does not tell us about the amount of load curtailment. That's why this index is not sufficient. We need to also quantify the amount of load which is not served. This is this we can know by this energy not served. This will add the amount, the energy, megawatt hour, the energy which is not served in these two instances. That we can calculate using energy not served. So together these two can tell us the number of events, number of hours where the load is not served, as well as what is the amount at that time. So both of them we can know by these two indices. In production cost modeling, if the objective is to also know the reliability standard, or what will be the reliability of the, how reliably the future load will be met, then we have to estimate these two indices also. We can also estimate other indices as per requirement, but these two are the most widely used. There are others also, loss of load hours and expected normalized energy not served, NENS. Loss of load events are also there. There are several indices, probabilistic reliability metrics. In this week, we have studied this probabilistic, this production cost models, and there are different types. That so we'll see that. Here you can see this production cost model. It is a computational model. Right? It is a computational model which calculates generation systems production cost. This we have been calculating in economic dispatch as well as unit commitment also. It calculates the generation systems production cost, energy import, availability of energy for sale, and as well as fuel consumption. All these things are generally done for long range system planning. The main application. These are different applications. One is long range system planning, fuel budgeting, and system operations. So if we go from bottom to top, then the time horizon it will increase. For system operation, it is on a real time basis. It is operation time horizon is very less. 24 hours, or it can be real time also, 15 minutes. But longer in system planning, it is for a long duration, for very far in the future, for maybe 10 to 30 years. So that we will also, and it is a it performs digital simulation considering representing all these things. Generating unit efficiency characteristics, fuel cost per unit of energy supply, system operating policies, then contracts for purchases and sales of both energy and power capability, and policies to model hydroelectric plants also. So solution offered by the technology we already discussed. We are trying to identify the solution and so and so the production cost model it can be of two types. That is right. This is not a exercise which is a part of the state estimator itself. This exercise is completed and it is corrected. The state estimator will give you knowledge. But in our case, what kind of experiences we are resilient is we must be detected and the state estimator correct. So that is the solution offered by the proposed technology, and also the salient features or advantages of knowledge, novelty of the proposed. Sorry for the disturbance. I have changed the place. I hope it is fine now. Okay. Yeah. So we were talking about production. Were you able to listen the last previous part only? Or should I repeat that? Okay. Shall we continue then? Okay. Where was I? Here. So production cost model, depending upon the time horizon, it can be deterministic and stochastic. Deterministic is generally used for short this operational uh, when power system operation we are considering, because at that time we know the real requirement, the real demand, and the stochastic is generally used for long-term studies. So here we consider that everything is known with 100% certainty. Demand is known. We have estimate of demand considering that it is 100% accurate. Then we also know that the availability of units. They are available with 100% certainty. There is no, what we say, there is no outage of the thermal units. In this case, deterministic, they are used for studying issues related to operation and near-term decisions. Even these near-term decisions, that means up to 1 week, generally up to 1 week. Although they are used deterministic, it is written here that deterministic model is used, but even for them also we can consider uncertainty. Actually, this is based upon the models. This book, Wood and Woolenberg, even the third edition came in 2013. So till that time, the uncertainty in the power system was not much, and it was not much considered for studying these different issues, even for these operational issues. For stochastic, we were using these different probabilistic methods, which we will discuss, especially the Monte Carlo one. But now these things have also changed. Several new methods are coming up. Different methods of incorporating these uncertainties have come up. There are different methods which are used now. Some of them, do you know some methods for representing power system or tackling power system uncertainty in optimization problems? There are different methods, like one is one is the most basic one is stochastic programming. And this uncertainty started with this capturing uncertainty. The first model was the stochastic programming. Then even in this also we have different, it can be also risk neutral and risk averse. We have different risk measures which are used. And you would have heard about portfolio optimization, which is mostly widely studied in financial studies, but in finance by finance people, but it is these risk measures have been also adopted by power system engineers to quantify the risk of load not met, and different types of risk can be associated. Then there is chance constraint optimization. Then robust optimization. Last is distributionally robust. There is one more, interval based optimization. Interval based optimization. Or there is information gap decision theory is one more. These are different methods. I'm just telling you so that you may, if you want, you can go through them. But here we are not going to talk about all these things. We are only talking here about the Monte Carlo for stochastic, or there are other also which we are talking, which we will see here. One is that numerical, and the stochastic methods also depends upon the data which we are using, whether we are modeling it, the problem in discrete fashion or on a continuous. We are using continuous functions. And for these two, the methods are also different. For continuous, we have cumulant methods. These are approximate methods which approximate the PDF by using these cumulants, probability density function. Discrete will, they have numerical methods, numerical convolutions. Here we have analytical methods. Here we need to do integrations and all. Here discrete everything will be in form of summation. Integration is replaced by summation in discrete domain. So based upon that, we have to, in discrete also, we have different methods, how we do these discrete analysis. So let us move to this. We're talking about these two methods. So first is deterministic, which is generally used for short-term period operation and near-term decisions up to 1 week. So it incorporates generation scheduling techniques in simulation model. And if online UC is performed, it can also be used in offline studies. Like, let's say I'm doing these simulations, and for each day, if I'm doing a 1 week simulation, for each day I'm performing unit commitment, and using that solution, I can take these decisions also. The output of this UC program can be used to make certain decisions. And let's say I'm doing unit commitment for 1 to 24 hours. One thing is to do unit commitment for 1 to 24 hours, then do the next unit commitment from hour 25 to 48. Do two separate unit commitment like this. Another is to do a unit commitment from 1 to 2 hour, then 2 to 25, then 3 to 26, so on, 4 to 27, so on. Last will be 25 to 48. No, it will go on. It will be one of them and so on. So it is a rolling. It's a rolling, or we can say, generally it is called a rolling UC with a window of 24 hours. For each 24 hours, we are successively calculating unit commitment. So which one do you think will provide a better result? First one or second one? One unit commitment for 21 day, or 23 unit commitment? Yes, correct. Second one will be more, but second one is more better because this is done on a day ahead basis, 1 to 24. For next day, we are doing a unit commitment. We are doing a unit commitment for the next day. But here we are revising it every hour. And every hour we can, it is possible to revise because our real-time market is also working on a 15-minute time interval basis. So that is possible to do. So the output of this unit commitment program can be used to make sell and purchase. So I think it was somehow sharing was stopped. I have again started it. I hope it is visible now. Yes. So purchase and sale decision, transmission access issues, and then operator control, even demand management can also be, these decisions can also be made. So if peak demand, let's say peak demand is occurring at some time, the 10th hour 10th, and we know that this is going to be a peak demand hour. And we also know that some generators are on maintenance. And we foresee that during this hour, the generators and the unit commitment solution gives us a solution that results in summation of generation less than equals to the demand for that hour. So in that case, one option is to curtail the demand. Another option is we can ask, we can manage the demand. We can, but there are some contracts like demand side management, in that we have different contracts, different ways to do that. So we can ask the utility or the big consumers to shift their demand if possible. There are certain ways of doing that. That can also be taken care by using the output of in commitment. Then stochastic one is used for long-term studies where there are no near-term operational considerations. Here we consider the generator outage and the load forecast error. And the load forecast error as well as the generator outage, they follow some probability distribution based upon the historical data. From the historical data, we can know what type of probability distribution these two follow. Generally, for this generator outage, we consider a uniform distribution for this. But for load forecast error, there are different. Generally, we use a normal distribution for it. From the historical data, we can know all these things. We can fit the PDF also to the historical data and then generate the probability density function. So originally, these future system studies, as we discussed here, these were the original studies which were performed using production cost model, but later they were expanded to possible to study the possible effects of load management, impacts of even fuel shortage, and the reliability. This we already discussed, the reliability of future system. How will the generation be able to meet the future projected load demand? So in this case, we try to estimate. We estimate the different indices, reliability metrics, and energy not served and loss of load probability. This is the program for planning, the single area energy production cost program for planning. So here what we do, we initialize whatever data we have, inputs which are, this is for T. So we start the study and the first thing is to read the input. To read all the data, whatever is there, and then the maintenance schedule is also known. The annual load model is also known. And then for each time instant interval, we need to account for the hydro plant, whatever hydrothermal coordination which we have studied. We can use it here. So we can modify the load to account for hydrothermal schedule and interchange context. So here, the whatever load profile we have, say we have load profile. So this load profile is this annual load profile. And this one we are modifying. The modified load profile is different. It can be something like this, anything generally. So this will be known after subtracting this hydro plant schedule as well as interchange contracts. Interchange contracts can be, it can even reduce the demand or it can increase the demand also. It depends upon the interchange. At different times, it will depend upon the time. Let's say it might happen that generally it will happen that during the peak hour, there will be supply from the interchange. Let's say we have an interchange here. This is some other area from where we are getting power during the peak hour. And this load profile is the profile for area 1. And during off peak hour, the area 1 might be supplying power to area 2. In both the cases, the demand profile will be altered based upon whether area 1 is receiving power or it is supplying. If it is supplying during off peak hour, then the demand in that case will increase. So this we can say is the net demand after hydro plant schedule and the interchange contracts. So during off-peak hours, the demand might increase if the area 1 is supplying to area 2. If it is not supplying, then it will remain same. But during peak hours, generally the net demand will be less because area 1 will be importing power from area 2. Both can be zero also, but if it is there, we have to take these two things into account. And then once the net demand is known, the schedule of pumped hydro and thermal plants is calculated. So this net demand is subjected to this like thermal plants and the pumped hydro storage plants. The net demand will be met by these two types of generators. And this is to be done for each interval. Whatever is the time horizon, the interval for the time horizon, it has to be performed for each interval. If it is one time horizon is 1 day, then it is to perform for each hour and so on. And then print the result if it is done. If not, then again continue. There are different types of load models which are used. There are, and depending upon the problem, type of problem which is under consideration. This we will also see again. There is one table. In the table we'll see. So one thing which we have to remember is that the load model must always be created in the model for the smallest subinterval involved in the simulation, because the data which is a input to the model, the data can be available at different time steps. The load should be available for the smallest subinterval involved in the simulation. Other data which are not available for subinterval, they can be assumed constant. But load should be available for the smallest subinterval. This is one of the application which is in the control center, and it is a operational problem. Operational problems a problem this production cost model in control centers. So The production cost model in the control center So it is a part of overall application program structure, and this production cost modeling are intended to produce short-term shorter term computation of production cost in order to facilitate negotiation of energy interchange and to compute cost savings in order to allocate economic benefits among pooled companies. So these are the two applications in the control center. And for operation, as we have already discussed, for operational problems, the model is a deterministic model, and the load model which is used is the actual load patterns that occur during the period under the study. And time horizon for this is 7 days. For fuel budgeting, the objective is to forecast the need for future fuel supply at specific plant site. And depending upon the plant site, the arrangement of fuel supply can be through different sources, like controlling the mining of coal or its production. So controlling the production or mining of the coal, or transportation of the natural gas, or even coal. In India, you'll find there are certain plants where the coal transportation cost is quite high because the thermal plant is quite far away from the actual coal mine or the production site. Khargaon plant is one such example in MP. It's near Indore. So there is no coal mine nearby, and the coal needs to be transported from Jharkhand, Chhattisgarh, and transportation cost is quite high. Therefore, the the variable cost of this thermal plant is quite high as compared to other thermal plant. Then another arrangement can be the contracts for fuel to be delivered to the plant. Model, in this case, the model can be deterministic or probabilistic. Because here you can see the time horizon is 1 to 5 years. If the time horizon is very large, it's better to consider the stochastic, because actually we don't know what is going. The load is uncertain. The load needs to be projected. The load needs to be projected for the next 5 years, and that creates and there is always an uncertainty associated with that. This is the table which I was talking about. Here, these are the different uses, and here even we'll see the types of production cost programs also in the next slide. Here you can see that for long range planning, we can use load cycles. We can use load duration or load duration or load cycle, as well as total energy or load duration. Similarly, for fuel budgeting also, these are required. But if we have load cycle, we can do only the allocation of pool saving weekly schedule. If we have only the total energy or total energy, then we can only do the long range planning. Cannot do carry out the other one. We cannot do fuel budgeting, operation planning, weekly schedule, or allocation of pool saving. All these green one. So when the load cycle is available, then we can use. Actually, this is for the load cycle. When the load cycle is available, we can perform both deterministic and stochastic models. In that case, implementation deterministic model is similar to implementation of ED and UC without considering any post outage rates of the generator units, and it is assumed that the load cycles are also known for the extended period with full certainty. While in the case of stochastic, the probabilistic representation of future load and unit availability is required. Their PDFs are used. And because PDFs are used, the expected values of production cost and fuel consumption are computed. Because it's probabilistic, so we consider different. We have different scenarios. For that, we have associated probability. So we calculate the expected values. Okay. And one of the methods of production cost modeling is this Monte Carlo simulation. Here, what are we doing? Here we do a detailed deterministic. We solve detailed deterministic programs. Just a minute. So Monte Carlo simulations are detailed deterministic programs with added feature that unit outages and deviation from the forecast, the deviation of load from their forecast values. So the load forecast error. Load forecast errors as well as unit outage. They are incorporated by the use of synthetic sampling techniques. And the sampling is performed on these PDFs, on the outage and load forecast error probability density functions. We perform sampling from these known PDFs by generating random numbers. Random numbers are generated at the regular intervals, which are used to develop sample results from the appropriate PDFs. So for load, we have forecast error PDF, which is used to determine the magnitude of load deviation from the magnitude forecast or the mean forecast. And for unit, the random for unit or this generator, for generating unit, the random number from PDF, it determines the status of the unit. It determines the status of the unit on forced outage, operating at full capability, and when coming back into a state where it is available if it was previously unavailable. So derated. So there can be several states in a plant because there are a number of units, but a unit can have also three, generally two. The simplest model is to have a two-state model for a generator where this represent, let's say, it has a forced outage at a rate of 10%. Then this is, let's say, this is the install capacity, and this is actually zero only. This is 0 megawatt. This is availability PDF, available capacity PDF, probability mass function. We can say it's a discrete. So this probability of our probability of generating installed capacity is 0.9, and probability of generating 0 megawatt, that is outage, is 0.1 here. So it's a two-state model. Either generator will be operating on installed capacity, or it will be operating at, or it will not be operating. There can also be a three-state model where this is installed capacity, this is 0 megawatt outage, and this is a derated capacity. Okay. Together their probability will be 1. If it is 0.90, it is, let's say it is 0.80, this is 0.10, and this is 0.10. And this derating can be due to failure of some components of the generator. And then other type of production cost programs are, one is this quick and dirty model. And let me just shift once again to the same place. Yeah, sorry for the disturbance. The first one is this quick and dirty model. As you can see, here we combine, it's a quick, and it will be a quick model, very fast computation time is very less here. But it is a dirty model, that means it will be a very approximate model. We are not incorporating all the details. It is a coarse model, very few details are incorporated here. As we will see here that it It uses the approximate generation scheduling techniques with load model that separate the week into weekdays and weekend days. We have weekdays and weekend days, and the entire year is class converted into is represented by only 4 weeks per year, one for each season. Okay, let us explain this. And then finally, weekly costs and fuel consumption are multiplied by the appropriate scaling factor to compute the total seasonal values. Let us see this. What is this? What does this mean? In a year, we have 365 days and we have 4 seasons. Let's say I'm just randomly dividing these 365 days into 4 seasons. Do not actually represent the numbers. Number might be a little different also, but let's an approximate days for each of the season. Let's say the season 1 has 100 days and this is season 4. This has 50 days, 150, another 100, it becomes 250 and 115. So these are the 4 seasons. Okay, now these are the 4 seasons which we have considered. And for each of them, we are considering 1 week out of this. In this, we consider 1 week, 1 week, 1 week, and 1 week. Or better, we can, instead of days, we can also divide the number of weeks into 4 seasons also. That can also be done. If we have 52 weeks, if we have 52 weeks, anyway we can do, then we can divide them into 4 seasons. And let's say, let us go with this only. And in this 1 week, we are considering 7 days and we are dividing them into weekday and weekends. Weekdays, weekend, weekdays, weekend, weekdays, weekend. If this is not all done, then also you can take entire week data, that is 7 days into 24 hours. We can simulate the entire week. Now, which week should be used for that particular season? That is also a good question. It's an important question. Which week are we going to use for simulating that particular season? Because in that season, one season is having around 13 weeks. Then out of those 13 weeks, which one will be that week? So if you want to calculate the cost for this season, then what are we going to do? Add the cost for the week, then multiply it by 100 by 7. So these are the number of days in that week. This is a scaling factor. 14.28 something. So this week will be the cost for this season 1 will be scaled by 100 by 7. It will be scaled by 50 by 7. This will be scaled by 100 by 7. And this will be scaled by 115 by 7. So these are the scaling factors for each of these season. Each of these week, we can get the seasonal cost by multiplying these scaling factors. Seasonal cost. Okay. Then complex. This was a quick and dirty model which can be easily solved. The computation time is very less here, but it will give you very approximate result. Then we can, another option is, these two are the two extremes we can say. This is one extreme, this is the another extreme. This is one extreme where we are not considering details. We are neglecting all the details, major details. And we are using a very simplistic model. On the other hand, this complex one is a very, it's the other extreme. We consider the dispatch for several interconnected areas. Here we are considering only representing entire system by one single area production cost program, as we have seen previously also. That flow chart was for single area production cost program. This flow chart. This is for single area production cost program, but we can model all the different interconnected areas, several interconnected areas that can be modeled. Then we utilize the power flow constraint. In addition to this, when the interconnection is there, we need to model the tie lines also. So we model the power flow constraint caused by the transmission interconnections to restrict the inter-area interchange levels. The network model, which have been used in this production cost model, they generally use the simplified models, but however, AC model can also be used. The network model, generally they use simplified models like using the penalty factors in the objective functions or using the DC OPF, DC power flow model. And they can also be modified by using the distribution factors based upon the DC model. This we will see, these distribution factors we will see in the future lectures. Like power transfer distribution factor is there. Then induction shift factors are there. And load outage distribution factor is there. All these things we can use. Generally PTDF is used, power transfer distribution factor is used for modeling this DC model, DC power flow. Another is to use only a transportation network. That means we only consider that for each node we only add this constraint that the incoming is equals to outgoing. Incoming flow is equals to outgoing flow. But for each interconnection, we do not ensure that the power flow is within its maximum and minimum limits. That we do not ensure. This is not ensured in a transportation model. Only KCL is satisfied. Or we can say the intelligence theorem. Conservation of energy. But that flow limit or the thermal limit on the lines is not modeled in transportation network. Here it is modeled. In DC power flow it is modeled. Then we can have this AC power flow also, but this is generally not used in production cost models programs. It is generally used in the security constraint economic dispatch unit commitment, the security constraint unit commitment, and purchase sale analysis. Then OPF is used to study the transmission power and reactive power flow pattern to develop prices for the use of transmission system. So these have different usage. When we generally go for the planning purposes, we have been using only these simplified DC model because the problem size becomes very large. And using the entire AC model or complicated models, the problem size increases and it becomes very difficult to solve them. And the computation time so increases exponentially. Now we will see the production costing using the load duration curve. It's a very good example. We will see how to make this load duration curve. So when do we use this? When the total energy when total energy is known, only the total energy content is known. When total fuel consumption, we can use this total energy information when we want to know the total fuel consumption and production cost, but we don't want to know about the chronological effects or the capacity. And the capacity or chronological effects, the ramping of the generators, their capacity or limit considerations, if they are of not importance, then only the total energy which was met for a day is sufficient to calculate the total fuel consumption and production cost. If you only want to know these two, production cost and fuel consumption cost, then only the total energy supplied by the generators is sufficient for each of the day or for a week basis, whatever the time horizon which we have considered. The granularity is not, or the you can say the more integrate details are not required, then we can use the total energy. But if we want to ensure capacity limitations, then load duration curve is used, which is constructed using the histogram of the load for a given time period. Now we will see, let's say we have these load values for 10 hours. These are the load values for 10 hours. So from these load values, we can generate a PDF. We can see a histogram or PDF. Using a histogram, we can generate 10 mega out of 10 hours appears for 5 hours. So its probability will be 0.5, right? Similarly, the load of 15 megawatt is appearing for only 3 hours. Its probability is 0.3. And load 20 is appearing for 2 hours. So its probability is 0.2 only. Summation becomes 1.0. So same thing is written here. The load 10, 15 and 20 megawatt and frequency is 5, 3 and 2. So these are the probability P of X. Then we can calculate the CDF. So this is PDF, discrete PDF. And we can calculate CDF, which means that the probability X less than equals to X. So probability that the load will be less than equals to 10 megawatt is 0. Probability, no, not 0. Probability that load will be less than equals to 10 megawatt, it is 0.5. Probability that the load will be equal less than equals to 15 will be summation of 0.5 plus 0.3 to 0.8. And then probability that the load will be less than equals to 20 is 1. This is a cumulative distribution function CDF. Then we have inverted load duration curve, which says that probability of load greater than a particular value. The probability of load greater than equals to 10 is 1. Probability of load greater than equals to 15 is 0.5. And probability of load greater than equals to 20 is only 0.2. This is inverted load duration curve. And this is CDL. Same thing, let us see here. Let's see, this is a chronological load curve. Simply plotting this load with respect to time. How is the load evolving over time? So this is T is equals to 1 hour, hour 2, 3, 4, 5, 6, 7, 8, 9, and 10. Chronological load curve. Then we make the CDF from here. This one. So we say that load will be less than equals to 10 is 0.5. This is 0.5. And probability that load is less than equals to 12 will be still 0.5. There is no point in between. Then probability load less than equals to 15 is 0.8. And probability load less than equals to 20 is equals to 1.0. And probability that load will be less than equals to 30 is also 1. It will remain 1. So this is the cumulative distribution function. Then we have inverted load duration curve, which is this. Probability that the load will be greater than equals to 10 is 1. It will be always greater than or equals to 10, as can be seen from the data. And probability that the load will be greater than equals to 15 is 0.5. And probability that the load is greater than equals to 20 is 0.2. Okay. So these are the three different curves, and you should know the difference between them. Can be quite confusing. This is one is chronological load curve, this is known to everyone. The important thing is to remember inverted load duration curve. These two are different, not same. You need to remember, and you can easily you can write this IDC is equals to 1 minus CDF. You can directly see up to here. This is 0. Right? This is 0 up to here. And so this is 1 minus 0 is 1. Then jump over here. 0.5. 1 minus 0.5 is 0.5. Sorry. Okay, 1 minus 0.5 is 0.5. Then it is 1 minus 0.8 is 0.2. and then 1 minus 1 is 1 minus 0 is after this is it is 1. The next is load duration curve. This is inverted load duration curve. Then what is load duration curve? So this is probability on the y-axis. If you multiply it by number of hours, so multiply this, 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 and this. Five, 3, and 2. Probability that the load will be greater than 2 hours. Probability that the load will be 20 megawatts. No, sorry. It says that the hour load. Hours for which the load is equal or greater than 20. So the load will be greater than or equals to 20 megawatt for 2 hours. And that the load will be greater than equals to 15 for 5 hours. And the load will be greater than equals to 10 for 10 hours. This is the thing which is mentioned here. Let's say we want to satisfy this demand of 20 megawatts and we have 3 generators also. Let's say we have 5 generators. In the order of their increasing capacity, in the order of their increasing cost, full load average incremental cost. Let's say the generator 1 can generate 6 megawatt, generator 2 can generate 4 megawatts, generator 3 can generate 3 megawatts, generator 4 can also generate 3 megawatt, and 5 can generate 7 megawatts. Let's say this is also 4, this is 4, and this is also 4, let's say. The total generation capacity which we have is 16 plus 22. The 2 megawatt will be spare capacity here. So here you can see, because this generator, these 2 generators are the cheapest, they will provide this load. We also call them as base load units. So these become our base load units. Then we have next 4 and 4 megawatt. So here we have this 4 megawatts here. Then remaining 1 megawatt, this will be 1 megawatt by G3 and remaining 3 megawatt here also. This is G3. So G1 no by G4. The G1 is occupied. This is completely utilized. G2 is utilized. G3 is utilized. G4 is utilized. And out of G5, out of 4, only 2 megawatt is used. We are using this 2 megawatts. This is G5. For G5, we are using 2 megawatt out of this, its capacity of 4 megawatt. So this becomes a, let me change the color. This color is not good. Maybe this color. Yeah, this is better. So this is G5. So 2 megawatts out of its installed capacity of 4 megawatt we have used. These we call cycling units. And these we call as peaking units, which supply this unit, this peak power. Here we can easily see this power, this area will be captured, will be met by these peaking units. We can easily see here these are coming only for 2 hours. This for this hour and for this hour. For hour number 2 and hour number 5, this peaking plant. Generally, these are the gas turbine plants, gas plants, because they can ramp up very quickly. Gas turbines. Then we can see up to this part is it was met by the G4 and G3. This area under this part met by G4 and G3. G3 and G4. Actually, out of this also, let's say one was met by G4 only. And only G5 consider only one of the peak. Because G4 is cheaper, so it is able to capture. We can say for this interval, for interval 2, the capacity factor of G5 is 0. Capacity factor is energy generated by the unit divided by number of hours multiplied by installed capacity of that unit. Here, energy generated is 0 at T is equals to 2. Number of hours is 1. Installed capacity is 4 megawatts. The capacity factor comes out to be 0. However, to this we can say capacity factor for T is equals to 2 is 0. But capacity factor for T is equals to 5 is, it is supplying 2 megawatt into 2 megawatt hour energy divided by number of hours is 1 and installed capacity is 4, capacity factor of 0.5. Okay. The problem with deterministic methods is in some interval the generator can have a capacity factor of 0 also, and also it is considered, it assumes that the base load units are available with 100%. availability. Their force outage rate is not considered here. That is another disadvantage. And the cycling units are loaded based upon their priority rank as well as the shape of this curve, this load duration curve. Because we can see these two are the cycling units. G3 and G4 are the cycling units. And the G3 is cheaper, so first of all it is utilized. And then G4 is utilized up to here. The same thing is written here. These are the disadvantages of the deterministic production cost models. First is the base load unit are loaded for nearly 100%, which is not practical. For large thermal plants, the forced outage rate can be up to 10% also, as high as 10%. Then the next also we discussed that the cycling units are loaded for period that depend on their priority rank and the shape of the load duration curve. The period depends upon the priority rank and shape of the load duration curve. With adequate reserves, the peaking unit of an interval have nearly 0 CF. We saw at t is equals to 2, the, uh, the CF is 0, and but these conditions are violated when FOR is considered, because if we consider the force outage rate of for generators here, then this 10 megawatt will not be completely provided by this G1 and G2. They might not be available, and in that case, if let's say this generator is not available, then we will not be even able to meet the entire load if reserves are not there. If reserves are there, although the load will be met, but this profile will change. Who will meet, which generator will provide what will change. The unit can be under force outage or can be under the derating state. So we saw this is if only force outage rate and is considered, then we have a two-state model. And if both are considered, then we have a three-state model for the narrator. There are these two methods of two techniques to handle the convolution of load distribution and unit CDF. Because we want to multiply these CDFs. We want to get a resultant probability distribution function. We have two different probability distribution function, one for load and one for generator, and even for each generator we have a load distribution probability distribution function. When we want to get a net probability distribution function, let's say for two generators, then we can get that by using the convolution. By convolution, because we know that PDF for a continuous function is this is the expectation, and PDF is minus infinite to infinite dx dv. This is the CDF, and PDF probability that x lies between x is dx. So we have a We know that CDF is this. And using this CDF, if we have two CDF and we want a resultant CDF, then we need to use convolution. Okay. For that we require convolution because let's say we have two discrete PDF. One is this, one is this. Let's say this means this is state one when it is operating at its install capacity. This is state 0. The probability of it is outage is 0.1. This is 0.9. Similarly, let's say this is 0.05 and 0.95. And this is state 1, state 0. This is for generator 1, generator 2. These are the probability distribution function outage for the availability of the generator. Now we want to know what will be the combination of these two PDF of these two generators together. Then we can easily see there are three states. Let's say the install capacity is 150. Then we can know there are only four combinations when both are on. One is on, second is off, first is off, second is on, and both are off. In this case, what will happen? Install capacity together they will supply 150. Here only 100, here only 50, and here 0. And we can easily calculate the probability. Multiply this 0.9 into 0.95. This will be 0.9 into 0.05. This will be 0.1 into 0.95. And this will be 0.1 into 0.05. These are the probability for each of these combinations. Finally, and this we get by convolution. When we do convolution, we will get all these combinations. That's why we are doing convolution here. And the techniques to handle convolution are two types. One is numerical convolution. This is for discrete, when we are using discrete steps for of load. And this is for a continuous load function. In this case, we use these different methods like based on cumulants, which approximates these probability distribution functions in Cornish-Fisher or Graham-Charlier series. Cumulant methods, all these things are there. And then numerical convolution, there are two types of method, and these two are classified based upon the way we do the convolution, the order of convolution. In the expected cost model, the generators are first convolved. Here, the load is convolved with each generator. And this resulting will be convolved with the next generator. And the difference will be taken to know the remaining, to supply the remaining load. So to supply the remaining load, next generator will be added. Similarly, the difference is taken here between the successive convolutions. Here, The generators are first convolved and then it is used to satisfy the load. The reverse, the order is reversed. Here, starting with load, here load is convolved later. The same thing is written here. This should be not here, and this also I will remove it. It starts the convolution procedure with the PDF of load pattern and successively convolves the generation segment in an order determined by the economics in order to compute successive distributions of unserved load. And then the expected cost method is order of convolution is reversed here. We will see one example here. We will start by the convolving generation PDF and calculating the expected cost to serve various levels of power generated by the system. Then total costs are computed by summing the cost to serve each load level in the forecast load model. The PDF of here we use two functions to make the table. You can do this in a tabular format. So first function is this PDF of a capacity outage of X megawatt is given by this PEX function. Here X is the outage, capacity on outage. This is the expected cost of serving a load K. K is the load magnitude. Now we will see one example of this expected cost method. This is an example where we have two units, unit 1 and 2, power output and they have installed capacity of 80 and 40 megawatts respectively. And the fuel input, and we can calculate the fuel input cost by multiplying these two. Then we will get it the fuel cost in dollar per hour. So simply you can multiply this 160 and this also will be 160 or 0. Fuel cost at 0 output. From this you can get the incremental cost curve. So incremental fuel cost is this. Incremental cost curve will be 160. F1 is 160 plus 8P1. And F2 is also 160 plus 16P2. Same thing is written here also. And P1 and P2 are also known that the outage probability of first generator is 0.05. And outage probability of the second generator is 0.10. And then we know these two, G1 and G2. We have G1 and G2, 11, 10, 01 and 00. These are the four combination because we saw in the previous slide also. Let's say this is the PDF of G1 available capacity PDF. This is probability of 0.95. This is 0.05 for G1 and for G2 it is 0.9 and 0.1. This is 0.9 is 80 megawatts and this is 0 megawatt. This is 40 megawatt and this is 0 megawatt. The outage PDF will be opposite. Outage PDF will be like this. Outage of 0 will be with the probability of 0.95. An outage of 80 will have a low probability. Similarly, here also outage probability is outage of 0 is 0.9 and outage of 40 is 0.1. These are the four combination. When both are available, capacity of 120 megawatts is available and unavailable capacity is 0. Here we are making a PDF of outage capacity. So this will give us an available capacity. So both are available, 120 megawatt. Unavailable capacity becomes 0. And first one is available, for 80 available, 40 is unavailable. And only second is available, 40 is available, 80 is unavailable capacity. And probability is simply, this will be 0.9 into 0.95. This will be 0.9 into 0.95 into 0.1, 0.95 into 0.1. This will be 0.05 into 0.9, 0.05 into 0.9. And this will be 0.1 into 0.05, 0.05 into 0.1, same. So this is the PDF for outage of 2 units. And this becomes the x greater than equals to x. Okay, CDF. Now we solve it for expected cost. The first unit is 80 megawatt unit with a probability of availability with available probability of 0.9 and 0.95 and so its outage probability will be 0.05. F1 cost, incremental cost curve is this 160 plus 8 P1 and let me change the pen color. Okay. The unit loading will be given by this, where L is equals to K minus S minus X, where X are the feasible outage combination, feasible outages. And here feasible outages is only 10 because we are not considering any generator for this expected cost calculation right now. My generator here, since S is equal to 0 here, so X is also 0. There is no outage. X is 0, so simply it becomes K plus X. So X is also 0 here. S is 0, so X is also 0 here. So L simply becomes K here. So it becomes point, and this formula for delta EC, increase in expected cost, is this PI, which is the probability of availability. Here this PI 595. This is multiplied by this capacity outage probability PDF. This capacity outage probability for X. X is 0 here. So you see P0 is 1.0. Probability that x is equals to outage is equals to 0 is outage is equals to 0 is 1 here because no generation is available here. There will be full outage. Probability of 0 outage is 1. There will be no outage. It is showing. Considering right now no generator is considered here. We're directly taking the load here. So k is equals to k is increased from 0 to the first zero to 80. So 0.95 into P into F1. X is 0 here. So P is 0 is 1. Fi into Fl. And L is equals to K is 0 to S here. And because we are using here segments of 20, 20, 20, 20, 40, 60, and 80. So here it is 0.95 into P, X is equals to 0. And FL, L is equals to K plus X. X is 0, so K is same as L. F1 40.95, P is 0, F1 6 is similarly up to this will become 0.95 into P 0 into F1 into 80. There is no outage here. The new value of dispatch capacity S is equals to 80. So this is for first generator we have considered. Means S is 0. This is a S represents the previously scheduled capacity, which was there was no previously scheduled capacity. We are starting with this generator itself. So this becomes the capacity outage probability table for generator 1. For outage of 0 outage, there is a probability of 0.95. That with 95 probability there will be no outage. And outage of 80 is with the probability of 5%. And for each of these, we calculated the here EC K is equals to delta ECK. Because before that there has been no scheduled capacity, so increment is same as the actual value. But when we will use the second generator, we will add, then EC will be this EC1 plus delta EC2. EC2 will be EC1 plus delta EC2. This will become EC1. Okay, that we need to calculate now. Now for unit to second unit, we have capacity as 40 megawatt, post outage rate of 10%, and availability is 0.9. That's why F2 becomes F2 is 160 plus 16 P2. L here is S here is previously scheduled capacity was of unit 1, which was 100 megawatt. Sorry, 80 megawatt. So L here becomes K plus X minus 80. And X can take values 0 and 80. So one thing which we have to remember here is L is equals to K minus S minus X for K minus S minus X lying between 0 and C. And it will be equals to 0 for K minus S minus X less than equals to 0 or less than 0, and it will be equals to C for K minus S minus X greater than C. So by using all these things, we can calculate here S becomes 80 here. We can calculate for first one if we see K is 0, S is 80, 0 minus 80, so it is negative quantity. X is 0, 0. It becomes 0. The L here becomes 0. That's why it is 0 here. And outage probability is of 0 is 0.05. Again, if we write if X is 0, this becomes negative. If X is 80 here, then K minus K is 0, X is 80 minus 80, it becomes S minus X. S is 80, this becomes 0. For 0, it is negative. X is, so it becomes 0. And here also, we are getting 0. So both it is 0. For X is equals to 20, we write K is 20, 20 minus S is 80, minus X is either 0 or 80. For 80, it becomes 20, L becomes 20, and for 0, it becomes negative, so it is 0. L equals to 0. and probability of outage of 80 is 0.05. Similarly, we can do it for others also. For k is equals to 40, we get f2 40. K is equals to 60, f2 640. K is equals to 80, we have f2 40. It cannot go beyond 40. F2 0 and f2 40. Here f2 20 and f2 40. And this is only f2 40. So this way you can calculate. Let us move to questions. First question is, what is the primary purpose of production cost model in the energy sector? So we have already seen this. The primary purpose for production cost model is to optimize the generation schedule. But there can be other purpose also that we have seen: reliabilities assessment, there can be fuel budgeting, even planning. But in all these things, this is inherent. Load forecast is the input to production cost model. It is not the output. Losses, generally production cost model is using DC models. The losses are not modeled in the simplest model. And this is totally different. Renewable energy project evaluation. Second is, which type of production cost program is commonly used for long-term planning purposes. And this we have already studied. We use this single area production cost program or production cost model. And these two are the types of probabilistic production cost model. Then next, what is the main use of load duration curve in the production cost analysis? It is to optimize the generation unit commitment. We have seen that also. And the load curve was like this. These are base plan, peaking, cycling units, and the peaking units. And if you know their incremental average incremental cost characteristics, you can easily find that. And which method is used for computing probabilistic production cost considering unserved load? That is, unserved load method is used here. Then in the context of production cost program, what does the term expected cost refers to? Here, the expected cost, this expected cost, we already know that in the probabilistic method, we need to perform the convolution operation, and depending upon whether the model is discrete or continuous, we have different methods. And for discrete, we have studied the expected cost method. First method, second one was this expected and the which one? Unserved load method. And this is the one. So in this expected cost model, because this is a probabilistic method, expected cost means expectation of the generation cost, which is the average value, mean value. It's the average cost of electricity generation. Then in the production cost program, what does the incremental cost data present? Even if it is not the production cost program, incremental cost data represent only one thing. The cost of unserved load in probabilistic analysis. Cost per hour at minimum loading level. No. Cost of transmission losses. No. Cost of unserved load in probabilistic analysis. No. Yeah, cost of generating additional. Can you see this is incremental cost? So what is the cost of generating incremental or supplying the incremental load or the additional energy requirement or the load? That will be the actual answer here. Next question is, what is the significance of the ordered list of loading segments in the production cost analysis? Yeah, if it is ordered in the ordered as per their incremental cost, then it will optimize the unit commitment process. Optimize. Transmission losses are not related to this thing. And how the spinning reserve capacity is already, it is decided, predetermined. Input, it is an input, not output. And then it represents incremental cost data also, as well as, because we see it is ordered in the list, in the ordered as per the incremental cost itself. So it's the input also, and the output will be the optimization of the unit commitment process. These two are the answer for this question. It was a multiple choice question. There were two answers to this question, not just one single answer. What is the main purpose of expected cost method? To determine the average cost of electricity generation. Expected energy demand, this is the input to the model. Transmission losses are not, this is also not relevant. It is to determine the average cost of electricity generation. Ninth is, which factor does the production cost analysis prioritizes in determining optimal generation schedule? Maximizing renewable integration, no. Losses are not considered. Grid stability and reliability. Reliability is there, but this optimal generation schedule is as per the minimization of generation cost. So these are all the questions for today. I hope if you have any doubt, you can ask later also. You can comment in the discussion forum also. I will upload these PPT now itself. You can go through this example. I have taken this from Wood and Woolenberg book itself. So please go through it and you can ask any relevant questions that you have. Thank you for joining today's meeting.